Hello chemistry students. In this section you will be able to recognize the differences between a titration curve for a strong acid, strong base titration and a titration curve in which one of those substances is weak. You'll be able to calculate the pH at various points in acid-base titrations, like the initial pH, the pH prior to the equivalence point, and the equivalence point, and after the equivalence point, and describe how an indicator functions in an acid-base titration. Let's start with talking about a titration. It's one of the most useful ways for determining accurately the quantity of an acid, a base, or some other substance in a mixture. You learned how to perform the stoichiometry calculations involved in titrations back in Gen Chem 1. In this chapter, the following points were emphasized regarding acid-base reactions. First of all, the equivalence point for a reaction is the point at which one reactant has been completely consumed upon addition of another reactant. So we need to make sure when we're looking at that we're looking at the moles of the substance. The pH at the equivalence point of a strong acid, strong base titration is 7. The solution at the equivalence point is truly neutral only when a strong acid is titrated with a strong base, and vice versa. If the substance being titrated is a weak acid or base, then the pH is not 7. And here is one example. When we have a weak acid titrated with a strong base, our pH at the equivalence point will be greater than 7. A weak base titrated with a strong acid will give us a pH less than 7. So when I have a strong base, I will have a greater pH. The strong acid, I'll have a smaller pH. Some more important points at the equivalence point are moles of acid will equal the moles of base. The pH of the equivalence point is the value at the steepest point in the vertical portion of the pH versus volume titrant curve. The end point is the point at which the indicator changes color, and our goal is to choose an indicator whose endpoint is as close to the equivalence point as possible. Our titration curve is when we plot the pH versus the volume of added titrant, and that could be our acid or our base. Typically this is in milliliters. 3 cases we're going to look at. We're going to look at a strong acid titrated with a strong base, a weak acid with a strong base, and a weak base with a strong acid. Our first example is strong acid with a strong base. And our example here is hydrochloric acid with sodium hydroxide. Let's look at 3 different ranges: the initial pH, the equivalence point pH, and the pH after excess base has been added. Notice that our pH starts at 1 when we have just hydrochloric acid. As sodium hydroxide is added, so this is when I have 0 milliliters of sodium hydroxide added. Then I start adding my sodium hydroxide, and we can see that slowly the amount of hydrochloric acid declines and the acid remaining is dissolved in an ever-increasing volume of solution. So our hydronium ion concentration decreases and the pH slowly increases. After all of the hydrochloric acid has been consumed, and the slightest excess of sodium hydroxide has been added, the solution will be basic and the pH will continue to increase. So we can see here at our equivalence point is when I have equal amounts of acid and base and my pH is 7. Then as soon as I add 1 extra drop of sodium hydroxide, we can see my pH skyrocket. Notice over here on the right the volume of base added. Notice how low my pH is for adding 10, 20, 40, even 45 milliliters of base, 48 milliliters of base, 49 milliliters of base. I'm still at 3, a pH of 3. And then that 1 milliliter difference took me from 3 to 7. And then 1 more milliliter of sodium hydroxide took me from 7 to 11. This breaks it down even further. At 49.98 milliliters of sodium hydroxide, I had a pH of 4.7. I add 1 drop of sodium hydroxide to get me to 50 milliliters. That took me to a pH of 7. 1 more drop, so now I have used up my HCl. Here is when I had equal moles of sodium hydroxide and hydrochloric acid and a pH of 7. Add 1 more drop of sodium hydroxide, 50.02 milliliters, and my pH went from 7 to 9.3. Let's find the pH after I add 10 milliliters of sodium hydroxide to my hydrochloric acid. We need to do the stoichiometry to figure out our initial amount of moles. So I'm going to look at my hydronium ion concentration. I know that I have 0.1 molar HCl and 0.1 molar NaOH. That's my 0.1 molar HCl and my 0.1 molar NaOH, and I had 50 milliliters of HCl. So if I took my 50 milliliters and turned it into liters, volume times concentration, I have 0.005 moles of HCl. Now when I add 10 milliliters is 0.01 liters. So 0.01 times 0.1, I have 0.001 moles of OH. That's my limiting reactant. So I'm going to subtract that, leaving me with all of my hydroxide being consumed. 0.005 minus 0.001 leaves me with 0.004 moles of HCl. Divided by my total volume, I had 50 milliliters of HCl, 10 milliliters of NaOH, so 60 milliliters total, which is 0.06 liters. So 0.004 moles divided by 0.06 liters gives me a concentration of 0.0667. The negative log of that gives me a pH of 1.176 when 10 milliliters of NaOH has been added. Let's look at what our pH is after 49.5 milliliters of sodium hydroxide has been added. I still have 50 milliliters of acid and it's still 0.1 molar. So I have 0.005 moles of hydrochloric acid. Let's look at the sodium hydroxide. 49.5 milliliters is 0.0495 liters and its concentration is 0.1. So that leaves me with 0.00495 moles. 0.005 versus 0.00495. This one is still smaller. So we subtract that, leaving me with no hydroxide and leaving me with 0.00005 moles of hydrochloric acid divided by my total volume. So 50 milliliters of acid, 49.5 milliliters of base, that's 99.5 milliliters or 0.0995 liters. Take my moles divided by liters, and that gave me a concentration of 0.0005025. I took the negative log of that and I actually got 3.298, so I rounded it to 3.30 for pH. So after adding 10 milliliters, I had a pH of 1.176. After adding 49.5 milliliters, I had a pH of 3.3. Let's see what happens when I go to 55 milliliters of sodium hydroxide. I still have 50 mils of HCl. I still have a concentration of 0.1, so I still have 0.005 moles of HCl. Let's look at our OH. After adding 55 milliliters, my volume is 0.055 liters times the 0.1 molar, so I have 0.0055 moles of base. Now my smaller number is my acid. That's my limiting reactant now. So I have to subtract that, leaving me with no acid, 0.0055 minus my 0.005 leaves me with 0.0005 moles of base divided by my total volume, 50 milliliters of acid and 55 milliliters of base is 0.105 liters. That gives me a concentration of 0.00476 molar. But now I have that as hydroxide because that's what's left over. The negative log of that concentration gives me a pOH of 2.32. So 14 minus that gives me a pH of 11.68. Notice how this skyrocketed. 49.5 milliliters of hydroxide, I had a pH of 3.3. Add 5.5 more milliliters and my pH skyrocketed to 11.68. Let's look at the titration of a weak acid with a strong base. And it looks a little bit different from the strong acid, strong base titration. Here we're looking at 100 milliliters of 0.1 molar acetic acid. And we're going to titrate it with 0.1 molar sodium hydroxide. So I have weak acid, strong base. Let's look at our initial pH. The initial pH is higher or less acidic than when I had a strong acid. Remember, I started back at a pH of 1 when I had a strong acid. After the sharp increase at the beginning of the titration, the curve only changes gradually, and this is because the solution is acting as a buffer. This will continue until that base overcomes the buffer's capacity. Then notice here that we have our halfway point, our half equivalence point. At this point, the concentration of weak acid is equal to the concentration of its conjugate base. We can see here that's our acetic acid. The concentration of the acetic acid is equal to the concentration of the acetate. So therefore, the pH is equal to the pKa. It's called the half neutralization or the half equivalence point because half of the acid has been neutralized. Then notice part C, the equivalence point. The equivalence point's pH is 8.72 in this case instead of 7 with the strong acid, strong base. And this is because all of the acid has been converted to its conjugate base when we added that sodium hydroxide, and now that equilibrium moves backwards towards that weak acid and produces hydroxide. And notice that the steep portion on this curve is shorter than the strong acid, strong base. This shows us just a little bit more of the significance of that half equivalence point. The half equivalence point here, if I were to follow it over, my pH is 4.74. And if I took 10 raised to the negative 4.74, that would give me a hydronium ion concentration of 1.8 times 10 to the negative 5, which, if I looked up the acetic acid Ka, should be equal to it. So at the halfway point or the half equivalence point, pH is equal to pKa. Let's look at a sample problem. Consider the titration of 100 milliliters of 0.1 molar acetic acid, weak acid, with 0.1 molar NaOH, strong base. What's the pH of the solution when 90 milliliters of 0.1 molar NaOH has been added to 100 milliliters of 0.1 molar acetic acid? We need to do our limiting reactant stoichiometry. Remember that moles is equal to the concentration times the volume in liters. So we know that we have our weak acid plus the strong base, and that's going to donate our hydrogen. So our one product is going to be acetate and our other will be water. So let's look at moles for our acid. We knew that we have 100 milliliters, so 0.1 times its concentration was 0.1. So we have 0.01 moles of acetic acid. We were told that we put in 90 milliliters or 0.09 liters of 0.1 molar hydroxide. So that's 0.009 moles. Our limiting reactant in this case, this is the smaller of the two numbers. So we're going to minus X or minus the 0.009 from both reactants and add 0.009 to our products, leaving me with no hydroxide, leaving me with 0.001 acetic acid and 0.009 acetate. That's moles. To get concentration, we need to do moles divided by liters. And I have a total of 190 milliliters, right? 100 milliliters of acid, 90 milliliters of hydroxide. So take our 0.001 divided by 0.190. That will give me the concentration of my weak acid that's remaining. And then I'm going to do the same thing for my conjugate base. That'll be my denominator. And then I just need to multiply it by the Ka of my weak acid to all get the hydronium ion concentration. Once I find out the hydronium ion concentration, to find the pH, I just take the negative log of that. So after adding 90 milliliters of sodium hydroxide, my pH would be 5.70. Part B wants to know the pH at the equivalence point. Well, we know that equivalence point means that we have equal moles of acid and base. Well, I know that I had 100 milliliters of acid and it was 0.1 molar, so I have 0.01 moles of my acid, so I would need 0.01 moles of my base. And if I had 0.01 moles of both my weak acid and my strong base, that means that I would minus 0.01 and add 0.01 of my conjugate base. So if I took my 0.01 moles of my conjugate base, and I would at that point have 100 milliliters of my acid, 100 milliliters of my sodium hydroxide, so 200 milliliters total. So if I took my moles of my conjugate base and divided it by 0.2 liters, I would have a concentration of that conjugate base of 0.05 molar. Now we need to do our hydrolysis, looking at the pH at our equivalence point. I take my conjugate base, my acetate, plus water. Since this is our base, it's going to be our proton acceptor, giving me my acetic acid, leaving us with the hydroxide ion concentration. My 0.05 molar acetate ion concentration goes in my initial, and obviously I have no acid, no base initially. I will lose X, gain X, leaving me with my equilibrium values here that will need to be plugged into my Kb expression. Now, in order to find Kb, remember that Kw is equal to Ka times Kb. Well, we know Kw is 1 times 10 to the negative 14th. And we know our Ka, or we could look up our Ka for acetic acid. It's 1.8 times 10 to the negative 5. So to do Kw divided by Ka will give me my Kb, which is what we need here. We know that Kb is going to be equal to x squared divided by 0.05 minus x. I can cross off the minus x because my Kb value times 100 is way less than 0.05. When I solve for x, remember x is my hydroxide ion. So the negative log of that concentration will give me my pOH. Therefore, 14 minus the pOH will give me the pH at the equivalence point. Why did I go back and use Kb here? Because I started with my acetate. That's the only thing left at equivalence point. I used up all of my acetic acid, and I used up all of the sodium hydroxide, and therefore the only thing left at that was the conjugate base. The conjugate base requires the Kb. Lastly, let's find the pH after 110 milliliters of sodium hydroxide has been added. Here I still have the same amount of acetic acid. Nothing's changed. I still have 100 milliliters and it's 0.1 molar, so I have 0.01 moles of acetic acid. But I changed hydroxide. I now have 110 milliliters, so 0.110 liters times the 0.1 molarity, giving me 0.011 moles. Now, this is my limiting reactant. 0.01 is smaller than 0.011. So my change, I'm going to lose the 0.01, lose 0.01, leaving me with no acid left, but leaving me with 0.001 moles of my OH minus. And because I'm left with OH minus, I can go right into calculating that hydroxide ion concentration. 0.001 divided by my total volume, 100 plus 110, is 0.210 liters. Gives me my hydroxide ion concentration. The negative log of that will give me my pOH, and then 14 minus that will give me my pH of 11.68. So far, we've looked at titrations that have been for a monoprotic acid with a base, like sodium hydroxide. In the case of a titration of a weak polyprotic acid, there are N equivalent points. For example, if I had a diprotic oxalic acid, that means that there are 2 hydrogens here, so there will be 2 equivalence points. The titration of a polyprotic weak acid follows the same process as a monoprotic weak acid. As the acid is titrated, buffering occurs until the last equivalence point is reached. So I start with 2 hydrogens, and it's reacting with that strong base. 1 H will be donated, leaving me with H2O, and leaving me with 1 less H, so that's my conjugate base here. Then that is now my starting point here, HA, so this is my acid reacting with the base. That H will donate to the OH, leaving me with water and leaving me with my conjugate base of A2 minus. At the second equivalence point, all of the acid has been converted to that conjugate base, A2 minus, and then the pH can be determined by Kb. So we've looked at strong acid, strong base, weak acid, strong base. Now a weak base with a strong acid, this process follows that of a weak acid but in reverse. There exists a region of buffering followed by a rapid drop in pH at the equivalence point. Let's look at a problem here. What is the pH of a solution at the equivalence point in the titration of 100 milliliters of 0.1 molar ammonia, weak base, with 0.1 molar hydrochloric acid? That's a strong acid. Well, remember, equivalence point means equal number of moles. So if I have 100 milliliters of 0.1 molar ammonia, 0.1 times 0.1 means that I have 0.01 moles of ammonia. So that must also mean that I have 0.01 moles of hydrochloric acid. So I'm going to do my 0.01, 0.01, and show that I'm going to lose those and have equal number of moles, so none left over, which means, let's look at my conjugate acid on the right, 0.01 moles of ammonia. That's moles. Now I need to do moles divided by liters. If I had 100 milliliters of ammonia, I would also need 100 milliliters of HCl, so 200 milliliters, which is 0.2 liters. I would have a concentration of 0.05 molar ammonium. But ammonium is not my hydroxide and it's not my H3O+. So to determine the pH, we needed to do the hydrolysis of this weak acid. NH4 plus water. This acid will donate a proton to water, giving me that H3O+. That's what I need to determine the pH of the solution. We lose reactants, we gain products, leaving me equilibrium values of x squared over 0.05 minus x. I looked up the Ka for ammonium, so I know my Ka is equal to x squared over 0.05. We can get rid of that minus x because 5.6 times 10 to the negative 10 times 100 is way less than 0.05. Solving for x gives me 5.29 times 10 to the negative 6, and the negative log of that gives me a pH of 5.28. The last part of this section is about pH indicators for acid-base titrations. You may have done an acid-base titration in the lab, and before you start the lab, you added an indicator, a couple of drops. It's a clear liquid. This indicator is usually an organic compound that is itself a weak acid or a weak base. And it's a substance that changes color at a specific pH. Many organic compounds, both natural and synthetic, have a color that changes with pH. Not only does this add beauty and variety to our world, but it is also a useful property in chemistry. Care must be taken when choosing an appropriate indicator so that the color change, which signifies the end point of the titration, is close to the steep portion of that titration curve where the equivalence point is found. Here's just one example of an organic natural compound. Here I have the pigment that's in rose petals. So in A, we can see that it's extracted with ethanol and it is a faint red. After I add acid to it, it turns a deep red. And after adding a base to it, NH3, it produces a green color. Here are a lot of different indicators for acid-base titrations. Phenolphthalein is a very common one. Its range of color change is between 8.2 and 10. Notice that its pKa value is right in between there at 9.4. Bromo blue is also a widely used indicator, with its range of color change being between 6 and 7.6. Notice its pKa value. Methyl red is also a very commonly used one, where it would change its color between 4.8 and 6, and its pKa value is 5.